Good morning. Welcome to Saturday Physics for everyone. I'm so glad to see all of you here today. Let's see. Welcome. Yes, this is our first lecture in our fall 2024 series, and we're pleased to welcome Professor Daniel Andruczyk to speak about fusion in this lecture. If you have not been to Saturday Physics for Everyone before, this is a public lecture series where our faculty members have the opportunity to share about their current research and for all of you to learn about what we're doing. Specifically, we're excited to have some high school students in the audience today. So if anyone has questions about what it's like to be a physics major, I can also help answer those questions. Let's see. So we will have 6 lectures in this series. This is the first one, and we will have a variety of topics. If you would like to sign up for emails, you can do so with the paper sign-up sheet, or there's a QR code that you can scan, and you'll receive updates about the lectures as they come in the semester. For this specific lecture, we will have the talk followed by some Q&A, and then it will be followed by a short tour of the Hydra, which is in the nuclear radiation lab right across the street. And that'll be about 30 minutes, and you're welcome to ask more questions during that time as well. So, without further ado, I will welcome our faculty speaker today. So, Professor Andruczyk is a research associate professor in the Nuclear Plasma and Radiological Engineering Department and heads the Hydra fusion device at the University of Illinois. As you will tell from his accent, he comes from the very deep, deep, deep south, Australia. Daniel was born and raised in Sydney to Polish immigrants. At the age of 15, he moved to Brisbane. He did his undergraduate degree in physics at the University of Queensland in Brisbane and completed his PhD in plasma physics at the University of Sydney in 2006, where he gained extensive experience in plasma diagnostics, including the development and running of a diagnostic helium beam to measure plasma temperatures and densities, which was installed and became an integral part of the H1NF HELIAC device in Canberra, Australia. He did his postdoc in Northeast Germany from 2006 to 2009 at the Max Planck Institute for Plasma Physics in Greifswald, where the W7X stellarator is located. While there, he worked on the Vinetta linear plasma device and the WIGA stellarator, where he specialized in diagnostics and plasma heating using OXB, or Bernstein wave heating. He also had a hand in integrating some of the control systems with the diagnostics on WIGA, which became integral in benchmarking and the running of W7X. In 2010, he came to UIUC as a postdoc, but quickly rose to be a research scientist and was stationed at Princeton Plasma Physics Lab from 2012 to 2014 for the university, working on NSTX and other fusion-related projects. This is where his eyes were opened to the world of plasma material interactions, and in particular, in fusion, the necessity for liquid lithium to be used. In 2013, an opportunity to move the WIGA stellarator to Illinois presented itself, and he was able to help secure its move here. He spent 8 weeks literally taking apart the entire machine in Germany, having it packed and shipped to UIUC, and then 18 months putting it back together again. In 2014, he became a research assistant professor at the Center for Plasma Material Interactions, and in 2021, he was promoted to research associate professor. Professor Andruczyk conducts research into plasma edge studies, in particular, the impact that PFC materials have on the performance of plasmas. He specializes in liquid metals, especially lithium, as potential future materials for plasma-facing components in fusion devices. The work he has made him one of the leading experts in the world when it comes to lithium interactions in fusion plasmas and liquid plasma facing component development. Daniel has run extensive experiments in reactors around the world on flowing liquid lithium systems, and this has led him and UIUC to being one of the lead PIs and lead institutions in the Department of Energy's domestic liquid metal PFC development, along with Princeton Plasma Physics Lab and Oak Ridge National Lab. As part of the program, Daniel and his team discovered, using Hydra, that lithium can solve one of fusion's most taxing issues, the helium problem. He has shown that lithium will effectively pump helium out of a system where most pumping systems will struggle, potentially solving one of the big headaches in fusion. He's also the director of the Nuclear Plasma and Radiological Engineering Department's Professional Masters of Engineering and Plasma Engineering program. He teaches several courses, including an introduction to plasmas and their applications, technology of gaseous electronics, plasma material interactions, fusion engineering, and 2 introductory courses to energy and energy sources. On a more personal note, Daniel is married with 2 young children. You might have seen them and all of their energy over there. He met his wife, actually, on the same day he secured WIGA to come to UIUC in 2013.
I was very efficient with my time.
Yes. He is fluent in Polish and speaks some German still. Even though he has lived overseas for 20 years, he is still passionate about his native sport, rugby league, and still follows his beloved Cronulla Sharks.
They made the semi-finals last night, so
nice.
I'm happy.
He has worked over the years with various countries to help establish the sport of rugby league. He even has a trophy named after him in Poland.
Mm-hmm. I'm called the grandfather of rugby league in Poland. Nice. So, yeah.
Daniel used to play tennis, but still enjoys watching this sport. While at university, he took up ultimate frisbee, where he established a club in Greifswald and coaching there. In 2021, however, he was diagnosed with tongue cancer and went through surgery to have it removed. It then came back a year later, and after surgery, chemo, and radiation therapy, has been able to overcome it. Excellent. He has now had nearly...
some good scars to show.
Yeah. Nearly 18 months with a clean bill of health.
Yep.
Congratulations. Daniel is also a home brewer and not only loves the science, but the art of brewing different beers, and is always experimenting with different flavors and styles, and grows his own hops for beer. Mm-hmm. Please join me in welcoming Professor Daniel Andruczyk.
Thank you. All right. Can everyone, I hope everyone can hear me. Okay, thank you very much. I'm so excited to be here and talk about something I've been really passionate about for many, many years, and that's fusion. And my name's Daniel Andruczyk, and I'm going to be talking about nuclear fusion and putting a star in a bottle. And I'm literally not kidding about that. What we are doing is making stars. Well, actually, I should mention it's not really a bottle, it's a magnetic bottle that we're doing. So this is going to be sort of like, I'm going to have a lot of background on fusion, because what I find quite often is that there's a lot of sort of misunderstanding on what fusion actually is and what it entails. And so I really want to give a good background of what fusion is, and then sort of dive into some of the problems and solutions that we have. Okay, so why do we need fusion? It basically comes down to energy. So climate change and all that, let's just put that to one side. Really, one of the big taxing things is energy and energy security. And why is that? So if you have a look at the United Nations Human Development Index, okay? And let's have a look at the United States here. So this yellow line here. And what do you notice is up here above this 0.9. So this is, sort of really good. This is what you want. You want a good life. 0.8 and above is sort of like, okay, you know, the developed countries. And the big link is that energy. The countries that have access to energy and cheap energy, right, for their population are the ones that have a really good, you know, life for their citizens. And, you know, this is also demonstrated here. Again, this is looking at the GDP of different countries, and you can see it's the developed countries, you know, the first world countries, if you want to call it that, that have access to energy, lots of energy, and they're also the ones that have, you know, make money, have the money, because they have access to that energy. They can do things, they can sell things, and make money. So energy is the crucial thing. Now, energy usage in the US has plateaued over the last 25 years. So if we have a look at this, the red squares here, you can see from about 2000, it's been pretty steady, okay? And that is because we've become more efficient with our energy use. So we haven't had to necessarily put more energy onto the grid in the US in order to make more products and more things that we can sell. Okay, and this actually is a feature that you see in many developed nations. So if you look at Europe in general, Japan, they've plateaued as well because of the efficiency. The thing is, that's not going to be the case always. Okay, at some point, as populations grow, you know, and energy usage needs to go up, you know, we're going to need to have a way to put energy back on the grid, right? And so the green triangles represent China. China is wanting to get up that curve on the Human Development Index. You know, they sit down the bottom. They want to get up to where, you know, let's say the US or Europe sit. So overall, though, if you look at the world, the world's energy usage continues to grow. So as developed countries in Africa, in Asia, South America, as they want to sort of get their populations also you know, up that Human Development Index, okay, it's going to mean that, you know, energy usage has to go up, okay? So that's why energy is so important, okay? But the thing is, our energy market in the future, okay, compared to what we have now, is going to look very different. And we're going to have to use everything at our disposal to bring that energy in. So fossil fuels will be part of the equation. You know, at some level, we're always going to have fossil fuels, okay? Not just for the production of, let's say, our electricity, but a lot of these fossil fuels go into the manufacture of the things that we need for a lot of the renewable sources. For example, the concrete that is needed, okay, to build all of these things, you need fossil fuels there for the manufacturing of the concrete. Things like solar panels, the silicon, okay, you don't just dig silicon out of the ground. It's usually bonded to oxygen as silicon oxide, and you need to mine the quartz, and you need to refine that quartz in order to get the pure silicon. The way you do that, you have to react it out with some coal, right, and get it out. And so fossil fuels and renewable energy, you know, so that they're still linked in some way, but they're all going to be part of that equation. Energy storage is also going to be part of that. Some of these are transient, so you need energy storage systems, whether they are hydrogen fuel cells, battery systems, or hydro systems. We're going to need that as well. And of course, we have nuclear. Right now, we have fission, and fission makes up 20% of the energy market in the US right now. And in the future, you know, what else are we going to have? And that's going to be nuclear fusion at some point. So the thing is, the exciting thing for me is that fusion though, is making its way into the public psyche a little bit. We see it in pop culture quite often. So I've got some show and tells here. Who knows what this is? Iron Man's arc reactor, little chest thing. I built this when I was going through my radiation treatment, through my cancer treatment, and I had this, built it sort of as, I was just, I had nothing to do during the days, while recovering, and just over a week or so, I just slowly put it together. But don't worry, there's no actual, this has just got LEDs in it. But yeah, in pop culture, we've got, we see in Iron Man the arc reactor. This actually, believe it or not, is a pretty good representation of what a fusion reactor currently looks like. You wouldn't necessarily use a glass, but this donut shape is certainly there. This was in one of the Spider-Man films. Doc Ock, right, was using his arms to manipulate a fusion reactor. I like how, so a little bit of artistic license there, saying, oh yeah, we're going to make a star literally in the room. A little bit of violation of some physics there, but that's okay. The whole point is that we're getting people thinking about fusion. Star Wars, we're all Star Wars fans, right? Well, I mean, it's fusion reactors that power the Death Star and all the spaceships and things like that, right? In the Saint, cold fusion made an appearance there, and also in one of the Batman films, there was a fusion reactor there that was part of the plot. And of course, one of the most famous ones is the core, the warp core of the Starship Enterprise in one of the reboots of that franchise. And the cool thing about this is that is an actual fusion reactor. That is the laser fusion reactor, the one that maybe you've heard recently got all the more power out than in the last year and a half. That is it. They actually used that as a film set for the for Star Trek. So that's pretty cool that they did that. Okay, so that's my little intro to this, believe it or not. So what I'm going to do is split the rest of this talk into 3 areas. I'm going to get into the basics of plasmas and fusion. How do we go about building an actual fusion power plant from there? And why don't we have fusion yet? Okay, that's a very important question. And it's a question, the main question that I get from people, when I meet them, they say, when will we have fusion? And that's a really important question. The running joke has always been, that it's always 50 years away, right? It was like that 50 years ago. It was like that last year. But now I think we're getting to the point where we can truly say, I think we're more like 15 to 20 years away to getting the first potential electricity going onto the grid. So, basics of plasmas and fusion. Now that question of, when will we have fusion? My simple answer to that is, we've had it for 13.8 billion years already, okay? It's the thing that drove the universe to be what it is, okay? And if you have a look at this picture here, really sort of here where it says the first stars, this is really where so within 400 million years, you had plasma basically out here, but this is where your fusion started to happen, where you started to get the stars. And we know that this is happening because we have a look at the galaxies, we have a look at nebula, we see all the stellar nurseries, and of course, in our backyard, we have the sun, okay? The sun is a big fusion reactor, a fusion furnace. So, let's go back to basics. Let's go back, a couple thousand years, maybe 3,000 years, back to the Greek philosopher Empedocles. right? So circa 450 BC, he is the one that came up with the 4 elements, right? Earth, fire, wind, and earth, okay? And what do these represent? If we think back to what do we know about the state of matter around us in the universe, we have solid, earth, plasma is fire, gas is wind, liquid is water, right? The 4 states of matter, the main ones. I've heard arguments now that there's actually 20 states of matter, but I don't know if I really want to believe that just yet. So how do we get this? So the way we're usually taught is that if you have something solid and we put energy into it, then it will turn into a liquid, and put more energy into it, we start to turn it into a gas, evaporate it. So think of water, right? We start with ice, it's solid. We put some heat into it, some energy, becomes a liquid. We put more energy, we start boiling it, we're getting it close to the boiling point, and we'll see that steam, that gas coming off. Thing is, if we put more energy, even more energy into that, we get a plasma, okay? That's usually the way we teach things. I make the argument that a plasma, okay, it's a state of matter, but I say it's the first state of matter. And again, back looking at this. It's the first thing that was there at the dawn of the universe. We wouldn't have every other state of matter if we didn't have a plasma first. So it went plasma, and then everything came after that. So my argument is plasma is the first state of matter. Now, what is a plasma? A plasma, in the end, is just an ionized gas. So or ionized matter, I shouldn't say gas. It's matter, because you can have solid plasmas and liquid plasmas. Now, so we start off with a nucleus, or an atom. So it's got a nucleus, it's got some electrons. This is like the outer electron that is orbiting around that nucleus. The nucleus has a plus charge, a positive charge, and the electron has a negative charge on it. And so we put some energy into it. So we put some energy into that, and if we put the right amount of energy, that electron will be ripped off the atom, and we now have basically free electrons and positively charged atoms, which we call ions, floating around. And they will be in a state not bound to each other, right? But they will be there, and they'll be subject to electromagnetic forces that are applied to them, around them. Where do we find plasmas? Basically everywhere. We find plasmas everywhere. So a flame, if you burn something, that's a plasma. If you have a flame, and if you've got a strong enough magnet, and bring that magnet, you can actually bend that flame, right? Because it's got electrons and ions in there, and some of those electrons and ions will bend, right? So aurora, who saw the aurora earlier this week? Yeah? There was a spectacular one in May as well. So auroras are plasmas. The plasma that gets ejected from the sun, some of that gets trapped on our magnetic fields, the electrons and some of the ions, and they will bounce back between the poles on the magnetic fields, and they interact with the atmosphere and excite the atoms in the atmosphere, and you get these beautiful aurora. Lightning is a plasma. Fluorescent lights. Do we have any fluorescent lights in here? Maybe in the back there somewhere. Okay, fluorescent lights. The solar wind, the core, solar core, and of course, fusion reactors. And it turns out somewhere between 95 to 99%, somewhere in there, of all visible matter is in the plasma state. So it is still the most common state of matter in the universe. Okay? So solid things like this are actually more uncommon than common in the universe. So that's the basics of plasmas. Now let's start getting into the fusion and what entails there. Fusion is a nuclear process. Okay, we're changing the atoms physically from one type of atom to another. So if we have a look at this plot here, this is a plot of the binding energy per nucleon. And what do I mean by per nucleon? In an atom, an atom consists of protons and neutrons. Those are called nucleons. They are in the nucleus. So this is the energy needed per each one of those in a core to bind it and hold it in that nucleus. So as you can see, it sort of goes up, up, up. It hits a peak around iron, is at the top, and then it comes down a bit. And so what we find is that if we go to the right of this curve, this is where we need to do fission. We need to split atoms if we want to get energy out. Okay? So we usually do this by firing a neutron. If you have fissionable material, it will then split, and it will basically, you start with uranium, it splits into things that are up here, and the energy difference is what gets released as energy. And we can harness that, make electricity, etc. On the left-hand side is where fusion sits. And it's the same thing, but here we need to bring things together. So if we, let's say we take deuterium, this H2 and H3 tritium together, okay, they will make helium up here. This energy difference is released as energy that we can potentially capture and do something, make electricity with it. Okay, so this is how the nuclear binding energies work, and why we do fusion with the light elements and not with the heavy elements. And of course, the driving thing, and I promise there's not going to be too many equations, maybe 3 or 4, but they're easy equations. But this is the one that everyone knows, E equals mc squared. This is the driving equation for when we get the energy. So the mass difference, from the uranium to whatever it breaks into, that mass difference relates to the energy. You get energy out. Okay, so we know fusion works. We have the sun. The sun's a big fusion reactor, so we know the concept of fusion works. So it's huge. It's a huge fusion reactor. Often, I get a question, how easy is it to build a fusion reactor? I actually say it's really easy. You get 2 by 10 to the 30 kilograms of hydrogen, stick it in one spot, and just watch it go. Gravity will do everything for you. Here, I want to point one thing out. Look at the average density of the sun is about 1.5 times that of water. People often say, it's a big ball of gas. It's not. The sun is solid. If you try to fly through the sun, heat aside, you're going to crash into the surface of the sun. It's pretty solid, the sun, right? And that's why I say it's, a plasma doesn't have to be gas, ionized gas. It's ionized matter, because you can have a solid or liquid type plasmas. And we see that on Earth as well. Technically, a semiconductor is a solid plasma. It's a type of plasma. It can be modeled as a plasma. So the sun has a fuel cycle where it changes hydrogen into helium. And what that looks like is, if we, here's a little legend here of protons and neutrons. Okay, it looks something like this. So we take 2 protons to make deuterium. So 2 protons being hydrogen. We take the deuterium and another hydrogen to make helium-3, an isotope of helium. And then another helium-3 come together from another path here, and we get the helium and 2 hydrogen come out. That's the fusion process that you get from in the sun. And we know this is the case because we can actually measure, looking at the light, coming from the sun. The helium is in there, the helium-3, and the helium-4, the regular helium. And actually, the moon, maybe you've heard that the moon has the largest amount of helium-3. It's a stable isotope of helium. And the moon has a lot of it in its rocks. And that's because this gets ejected out of the sun. The moon doesn't have a magnetic field to protect it the way the Earth does. And so that helium-3, as it hits the moon, will lodge itself into the crust of the moon and stay there. Now, on Earth, we do not have the luxury that the sun has. That's gravity, to do things for us. So that hydrogen reaction I just showed you there, we can't do that here on Earth. And there's other reasons for that, and I can maybe in the Q&A, if someone's interested, I can sort of talk about it. But what we do is we take the two flavors of hydrogen, deuterium and tritium, and we use those as our fusion reaction. So the reaction is deuterium plus tritium gives me helium. A neutron comes out, and there's this 17.6 MeV of energy. You might be thinking, what is MeV? Right? This is what we call an electron volt. So MeV is a mega electron volt, millions of electron volts. So it's just another unit of energy that we use to discuss more conveniently larger small amounts than the numbers with other energy when we talk about joules. So to give you some context, 1 electron volt, and you can see it's 1.602 by 10 to the minus 19 joules. Now that's a mouthful, right? So that's why we sort of convert this to this MeV unit, because 17 MeV is much easier to say 1.609 by 10 to the minus 19 joules every single time, right? And this translates to a temperature, and temperature is just a measure of energy when we talk about temperature, is about 11,600 Kelvin. And to give you an idea, room temperature is about 1/40th of an electron volt. The surface of the sun is only half an electron volt. A fluorescent tube is 3 electron volts. In a fluorescent tube, it's about 33,000 degrees inside of there. And you might be thinking, how is that not melting the glass? And it's because of the way we run the plasma. Most of the energy gets deposited into the gas that's in there, and the energy that does make it out to the wall, it does heat up, obviously, but not to the point where the air around it can convect the energy away and keep it, so it doesn't melt on us. Lightning is about 10 electron volts. So lightning gets to, can have temperatures going close to about 1,000,000 degrees in there. And then the core of the sun is about 1,300, so electron volts. So 10 eV, that's going to be about 1,000,000 degrees. Yeah, 1,000,000, and we're talking in the core of the sun, we're starting to get to close to 10 or 15 million degrees in that. Okay, so what is needed for fusion? There are 3 parameters that we need for a fusion reaction to happen and to sustain itself. The first thing is temperature. Now I'm going to give you a spoiler alert. Inside the fusion reactors that we have to run in excess of 100 million degrees inside the reactors, okay? We run 10 times hotter than the sun, the core of the sun. So temperature, we need density. We need to have enough stuff in there. Now, atmosphere is too much stuff. So we do operate in vacuums, right? So if you think about that picture of Doc Ock with the sun, that can't happen because the energy losses to the air would be too much. So we need to go to vacuum systems, and then be very careful with how much stuff we put into the vacuum to get the fusion reaction to happen. So there's a fine balance there. And then we have to store the, not necessarily the plasma, but the energy that is in the plasma has to be stored for just long enough for us to get fusion to happen. So we call this the energy confinement time. So those are the three parameters, okay? So temperature, why do we need something hot? Well, we have ions, right? Positively charged atoms, right? What happens when two charges of the same charges come together? They repel each other, right? But if you give them enough energy, you can overcome those cooling forces, those repelling forces, and actually bring them together, not just overcome that repulsive force, but you can overcome the strong nuclear forces, the quantum mechanical forces that make them into a new atom. So you can fuse them together to make a new atom. Dense enough. So if you don't have enough stuff, okay, the ions are just not going to interact. You're not going to get enough interactions. So you need to get them to the point where there's going to be enough stuff and you get enough reactions happening. Now, you can go too far the other way. You can get too much stuff in there where there'll be too many of these collisions and you're bleeding the energy away and you're just not keeping the energy in that plasma for long enough. And then confinement time. And again, the energy does get lost through various means. Diffusion, so diffusion is just the movement of the particles. Okay, the particles are carrying the energy. If you start losing those too quickly, you lose your energy. There's radiation effects. And when I say radiation, it's usually like photons, electromagnetic, so light. Sometimes as X-rays or microwaves and RF waves, but also just visible light. So that's another form of energy loss. So we need to make sure that the confinement time is such that we're making enough reactions and keeping that energy for long enough in the reactor so we're overcoming any of the losses, right? So we want to have sort of that confinement time be greater than the diffusion time that we're losing energy to, say, to the wall or something. So why this DT reaction? So there's our reaction there. Deuterium, tritium going to helium and a neutron. And the thing is, there are a whole bunch of other fusion reactions we could use as well. Okay? That's not the only fusion reaction. There's a whole bunch of them that we could use. But why are we focusing on DT? And it's because of this curve. This here is basically tells you the probability of the reaction happening. And if we have a look, the DT reaction is the blue curve. Okay? It has the highest chance of any of the fusion reactions that we have of fusion happening. That's why we do it. It's got the best. And at the temperatures here, this is in thousands of electron volts, so this is where we tend to operate. It's several orders of magnitude, so almost 3 orders of magnitude better than the other reactions, the other two closest reactions that we have. So the other ones are the deuterium-deuterium reactions. Some people are exploring that, but you have to really go to some other extreme measures to get that reaction going. And then another one that some of the private companies are talking about is doing this deuterium-helium-3 reaction. But again, the chances of it happening are much lower at the temperatures that we need to operate. So taking those three things, the temperature, density, and confinement time, we can actually do a little bit of math, right? do something called a power balance, and we come up with something called the triple product. And you can see here, this is why we need those three things, right? Because together, we can actually benchmark or have what the minimum is that we need in order to have a sustained fusion reaction, where the energy out will equal, at least will equal the energy going in. That's what we call the break-even point, or the Q factor. So you'll see this large Q, energy out over energy in, and you want that to be greater than or equal to 1. In fact, you do want it to be greater. I mean, equal to 1, okay, great. You know, but you're not gonna make money selling no electricity. So it'd be nice if you can get to a Q of 2, right? And so it turns out the minimum value that we need is this triple product needs to be greater than or equal to about 1 × 10⁻21 cubic meters, kilo electron volt seconds. And if you put the numbers in, our confinement time only needs to be 1 second. 1 second, that's all we need. We need to hold that energy in the plasma for 1 second, enough, okay? Turns out 1 second is an eternity for a plasma, where things operate on the nanosecond and microsecond scale, level. And getting to that 1 second has been tremendously difficult. We can get the temperatures that we need. We can get the densities that we need. But that confinement time is the thing that has really been difficult for fusion. So for a self-sustaining or a burning plasma, it turns out, this value here represents this Q equals 1, okay? And it's not really a self-sustaining or burning plasma yet. We actually need to get to a Q equals 5. And the reason that is, when you look at the way the energy gets split between the resultant helium and neutron, the helium only takes about 20% of the energy. 80% of the energy goes into the neutron, and that neutron does not have a charge, so it will be lost. Well, it doesn't get lost, we capture it and use it, but it doesn't go back into heating the plasma. The helium does. We capture the helium in the reactor and we use it to keep heating. But because it's only got, a fifth of the energy, 20% of the energy, we need to make that up. So we need to make sure we've got 5 times that energy to get to the point where we can switch off all the other external heating systems and just have the plasma sit there and what we call ignite itself. It will ignite and it will just maintain itself. It will burn as long as we've got the fuel in there, right? So literally, it will, at that point, it becomes a star. Right? A star, the sun, is just a self-burning fusion reactor. But it turns out that this Q equals 5, this is really what we call the scientific Q. Yeah, this is where engineering comes into it. This is what I do. Okay, this is the Q that's happening in the reactor, but when we go through everything and we have to build the reactor and extract the energy, there are efficiencies and energy losses along the way. By the time we get to the grid, okay, it's a different Q. So there are different types of Qs. There's the scientific Q, okay, what happens in the reactor. There is the engineering Q, what happens after we've extracted the energy and got to the point where we can start generating electricity. And then there's the electrical Q, which is what we actually do, the energy that we can actually put on the grid and sell as electricity and make some money off it. And some of that you're producing, okay, goes back into running the plant, all right? Your power plant has to have energy to run everything. So it has an energy budget, which you have to compensate for, and then you have to make extra on that you can sell. So it turns out that if we want to do that, if we want to have this Q electric of 2, if you work back to what we need back inside the reactor, we need a Q scientific of about 20. And that just starts becoming mind-boggling, just how big we need a reactor to be. in order to do that. And that's sort of one of the challenges that we have, one of the engineering challenges we have in fusion. So that's where you need to go. Q Scientific of 20. We haven't even got to 1 yet. Well, at least not in the magnetic. The laser guys have got that, but that's where we need to go. Now, the first ever Q greater than 1 fusion device, and I'm going to end this section on this, is, it wasn't an energy one, but it was the hydrogen bomb. The hydrogen bomb is a Q greater than 1 fusion device. It's just that, it was a weapon. Now, here's the thing. Yes, it was built as a weapon, but a fusion reactor, the technology behind fusion reactors, you can't make weapons out of that. Actually, the way it's all done, you can't back engineer, let's say, a hydrogen bomb out of a fusion reactor. So that's why fusion actually, unlike some fission technology where it's very secretive, fusion is very open across the world between even countries that maybe politically might not be friendly, but when it comes to the science of fusion, are very friendly. They're always talking and that. Just last week, a bunch of my students were in China at a conference and looking at the Chinese machine. All right? Politically, right now, okay, there's some tension there, but from a scientific point of view, no problem. So that's the nice thing about fusion. Okay, so that's that first section. Oh, yeah, and 10.4 megatons of TNT was released in that, with that explosion. They destroyed the whole island, like literally blew a hole where the island was. So how do we build an actual fusion power plant? So I've talked about what goes in, the basics of fusion, but I haven't really talked about how do we actually do this? How do we build one of these things? Okay? So we need to hold on to that plasma. Okay? So we need that confinement. All right? So there's a confinement time, but we need to hold the plasma in something. Okay? And so we have we get a vacuum vessel and that. Now we can make a plasma in just a plain old vacuum vessel with nothing else, and you'll create it. But you'll never be able to get to anything more than 2 or 3 electron volts, right? But you can still do something useful with that plasma. It's called microchip manufacturing, and every process along the way, when all the microchips are manufactured, plasmas are used at every single step of the process now to manufacture microchips. But they do it because they don't need to confine it. They don't need to go to the really high energies that we need. So it's a plasma. It's got electrons, free electrons, and ions. And so we can apply a magnetic field that will trap them on those fields. This is where that magnetic bottle idea starts coming in. We can trap them and hold them, and we can shape that magnetic field, okay, to start confining things. So some of the first fusion machines were these, what we call mirror machines. And what they do, they have a magnetic field that confines, and then at the ends, they would have an even stronger magnetic field, okay? And some of those particles would come in, and as they come in towards the field, they get reflected, and they bounce, and then they bounce, and then bounce, and they would get confined. The thing is, eventually, you do get end losses. If they come in at a low enough angle along here, you won't get that mirror, what we call the mirror effect, and that you will still get end losses. Now, this bouncing from one magnet to the other, what does that remind you of? Sorry? Pong? Yeah. No, but Aurora, the Earth's magnetic poles, right? That's literally what it is. So the Earth's magnetic field is a mirror field, right? So at the poles, the magnetic field is much, much stronger than, let's say, at the equator. And so the charged particles, the reason they bounce from one pole to the other, producing those beautiful auroras, is because of this, what we call the mirror effect. So, how do we stop those end losses? Well, we make this, a donut. The technical name for a donut is a torus. I dare anyone to go into Dunkin' Donuts and order a box of Tories. So the plural for toruses is Tory. So say, I want a dozen Tory, with everything on it. So yeah, who wants a donut? There you go. Have yourself a fusion reactor. So we bring it in. We bend it in on itself, and we have a donut-shaped field. We have the magnetic fields, and so we have a magnetic field here. Here's the thing. It turns out the magnetic field on the inside is much stronger than on the outside, and even though we have these magnetic fields, the electrons and ions are going to drift across those magnetic fields and hit the wall anyway, and there's nothing we can do about it. The laws of physics say that will happen. Okay? So what we need to do is find a way of producing another magnetic field that we can add to this one where we can flip these particles that are drifting towards the wall, and we flip them back in. Sort of like a magnetic spatula, I guess you could call it. Right? And the way we do that is that we drive a current in the plasma. Right? So when you have a conductor, right, you put a current through it, you will get a magnetic field, what we call a colloidal field, being produced. The easiest way to do that in a reactor is to do this, to make this colloidal field, and then to get the twisting field, is to make the reactor basically into a transformer. Wrong transformer, sorry. That one. One of those. Okay? Basically, we can have, we have a donut. We can put, say, a yolk. So imagine, the plasma, the reactor, represents one part of this coil. The plasma basically is a coil now, all right? And we can have what we call a primary coil, where we can put a pulse of current through it, and that will then drive a current in the plasma, and we get ourselves a colloidal field that will then work with our toroidal field. So if we do that, okay, so we get our plasma, it produces this colloidal field, that then adds together to give us this twisting field, okay? And it's not like a really sharp twist, but it's a gradual twist. It's enough, that once or twice as it goes around, we just push these particles back into the center, okay? And eventually, we can put that in a vacuum vessel, and build ourselves a fusion reactor. Now, there's several types of fusion. There's lots of different types of fusion reactors out there, different designs, but I'm going to concentrate on three here. So the first one is a tokamak. This was a Soviet invention. So it stands, well, if you try to say it in Russian, Torodanaya kamera z magnetymi katuszkami. I speak Polish, but I find Russian to be very difficult sometimes still. It just basically means toroidal chamber with magnetic coils, tokamak. And, basically looks like this. Okay, and the first time it was shown to the world was in 1968, but it turns out that the Soviets had been building these things since 1954. Let me have a... So, what's the anatomy of a fusion reactor here, of a tokamak? So we have our torus, the vacuum vessel, the donut-shaped vacuum vessel. Okay, we have our toroidal coils that are producing the toroidal magnetic field that goes around the donut, okay? We have something called the central solenoid, or center stack, sometimes we call these, okay? And so we put the primary current into this, okay? It will generate a plasma, and as soon as you generate that plasma and you've still got the current in through here, a plasma current will be driven, and we produce a poloidal magnetic field, which adds together to give us the helical field, and that's how we can find the plasma. And then we have poloidal coils as well, which helps to steer the position of the plasma inside. Question? No, we evacuate, and then you can either bleed the gas in, or these days they actually will fire little pellets, frozen pellets of hydrogen in and zap it with microwaves, cause the plasma, and then they can do that. And with the way computer systems are these days, they can track the progress of the plasma down to like the micro and even nanoseconds, and they can see when they need to maybe fire some more fuel in just to maintain the density levels and everything in the reactor. So this is the tokamak. So basically it's a transformer. Simple to build. And I do that because it turns out tokamaks are not that simple to build. All right, stellarator. The stellarator is a US invention. And actually, personally, I think it's, in the long run, all fusion reactors are going to end up being the stellarator design. But basically, it was a Lyman Spitzer, an astrophysicist out at Princeton, who came up with the idea. And there's a long story about this. It involves a little bit of, someone in Argentina sort of hoodwinking the Argentine government out of some money and basically claiming he got fusion but didn't. It basically was a bit of a scam. But it got Lyman Spitzer thinking, okay, how would we do this? And he came up with this design. For those of you that are going to come and see Hydro, this actually is the design of Hydro. This is what we call the classical stellarator. And the big thing that you notice with this is that there's no central solenoid. We don't need to make a stellarator into a transformer because all the magnetic fields are done externally. So we still have these toroidal fields, but now we have these what we call helical coils, which when you run the current in opposite directions will add to give you that poloidal component, which then can add to give you the twisting field, right? So 1953 was when he came up with this, and this was part of Project Matterhorn. This was actually sort of part of when the hydrogen bomb stuff was being done, the base for Project Matterhorn is what is now Princeton Plasma Physics Lab, the national DOE lab for fusion. So the anatomy here, we've got the torus, the vacuum vessel. Okay, we have our toroidal coils and our helical coils. Of course, we get the magnetic field, the twisting field that gets produced, and our plasma. Now, to do this, because we don't have that pulsed current to produce the plasma, we have to externally make the plasma now using other fancy systems like microwave and RF systems and things like that. But that's fine. That's actually turns out to be really easy to do. So the big advantage of a stellarator is because we can just run a DC current into our coils because they're all external. You switch it on and it stays on for as long as you want it. A tokamak, think about how a transformer works. It takes AC power to do that conversion. So in order to drive that current in the plasma, we have to put a pulse in. So by design, tokamaks are pulsed machines. And this is why I say that, okay, they look easy to build, but this is where they get complicated. Because once that pulse goes away, and that pulse is maybe only a couple seconds long, that's about the best we can do. We now have to come up with all these exotic other ways of trying to sustain and make the plasma continuous and last for thousands of seconds instead of 1 second. And that's where the complexity comes into the tokamak, whereas a stellarator does not need that. Just put DC current in, switch it on, and it goes. Okay? So, no plasma current. And that's the big thing. And that also helps with stability of the plasma, which I can talk a bit more about maybe in the Q&A. So, our own reactor, Hydra, is one of these classical stellarators, but with a quirk of history. It also has a central solenoid, so it can also work as a tokamak. It's the only machine in the world that has the capability of running both types of fusion reactor. There's no other machine that has that capability. And right now, we run mainly as a stellarator. We don't have the tokamak part hooked up, but when it was in Germany, they did occasionally do that, and they ran both the stellarator and tokamak part together, which is interesting. This is a YouTube clip that we took when we were putting the machine together. I'm not going to play the whole thing, but you can go on YouTube and watch it. And so this just shows, this is a time lapse over about 10 days of us putting the machine back together. So there really was a great effort by students in the facilities here at the university to put it all together. And we do have a little toy Hydra somewhere here. We play a Where's Waldo. There we go, there he is, right down here. He's gone. And so that is hiding behind the, right? So we do a little, I would say, see if you can spot Hydra in. It should be in every frame somewhere. All right. The other type is inertial confinement. And this is mainly laser driven, okay? And they take a little pellet about 1 millimeter in diameter. That's got all the fuel, the deuterium, tritium fuel in it, right? And they put it in something called the hull room. Okay, it's usually made of gold, okay? And they then take a bunch of lasers, I think it's something like 192 lasers, and they fire it down into the hull room. They literally pack into that 192 laser beams, which actually then on the inside blow the gold. The gold produces X-rays, which then focus back in onto the little fuel pellet and compress the fuel pellet in order to get the fusion to happen. Also not an easy type of design. But they've been quite successful. They've actually been able to get to the point where their Q scientific is greater than 1. I think their record's about 2 point something, which I have that sort of coming up. So how will a future power plant look like? And this is basically it. So you'll have your torus, right? You'll have some sort of systems bringing things in, right? So you'll have your helium will carry 20% of your energy, 80% of the energy is in the neutron. So that helium goes back into heating your plasma, but the neutron then will go into something called the breeding blanket, okay? And basically heats up the blanket. We extract the energy through some sort of exchange units, and that will boil either water or maybe heat up a gas or something like that to high temperatures, and then we can drive a turbine and make the electricity that goes in the grid. Basically, fusion is just another fancy way to boil water in the end. Just like fission, just like coal, that's all we're doing. We're boiling water so we can produce the steam that will make the electricity through turbines. So we need plasma heating, We need magnetic fields. These are sort of the 5 things that we need for this to happen. We will need to do the energy extraction, the fuel production. So it is a breeder reactor. Fusion reactors have to be breeder reactors. If they're not, we will never have fusion. And I'll explain why in a second. And then energy delivery. So those are the 5 sort of, pillars of what a fusion reactor needs to do. So the first thing, plasma heating systems, it'll be mainly through particle heating. Okay, so we use something called neutral beams. Okay, these things are truly huge. They can be as big as the machine itself sometimes. Then we have the alpha heating. That's the helium that we produce from the reaction goes into it. Okay, so that helium is very important in keeping the plasma hot, but eventually we have to get it out. Okay, once it's dumped its energy and it becomes cold, it becomes an impurity, and we have to get rid of that helium, and it becomes a problem. Also, electromagnetic waves are the other main way we're going to do it. So radio frequency and microwaves. And so we have large, fancy systems for doing that. And when you put all those together, this is sort of what it looks like. Okay? There's a reactor, but you can see the heating system's just as big, if not bigger, than the reactor itself. So it's truly, truly a massive undertaking what fusion needs to do. And part of the half the battle with engineering is how do we make this affordable and small? Because if we have to build a fusion reactor for $50 billion, no one in their right mind is going to buy one of those and build it and make electricity off that, make money off that selling that electricity. So magnetic fields. So here you can see sort of the blue coils there, electromagnets. They produce our toroidal fields. Under this brown, this grayish resin that are the 4 helical coils, right? And so, and here, this is a picture. I was actually at ITER earlier this year in May. I was in France. I went to visit, so this is one of my photos where they're building they're constructing the magnetic coils. And this is the plasma inside Hydra, what it looks like when we run it. And you can see it's really trapped. It sort of sits there. It's not going all the way out to the edge, right? It sits trapped in that magnetic field. All right, fuel and energy production. So what needs to happen is that we need to initially make the tritium, and that tritium is usually made in fission reactors. So we're very dependent on the fusion industry right now. Right now, there's only 30 kilograms of tritium in the world. Half of that is tied up in nuclear weapons. The other half, all right, is in labs and that for experiments and that. But the startup of a fusion reactor uses about 1 kilogram. So that means right now we only have enough tritium for 15 fusion reactors, or 15 times that we can switch a fusion reactor on. And so the reactor needs to be able to make its own fuel, its own tritium. Deuterium, we've got 15 billion years worth of deuterium on Earth, right? It's tied up in water. And we've got more than enough water to supply us until the sun explodes and wipes us all out. So that's not the problem. Tritium is the problem. So how do we do this? All right, so we start off with tritium and deuterium, the reaction. We've got the helium. This neutron gets captured in the breeding blanket. So we have this breeding blanket. Right now, the favored design is using a liquid metal. It's a mixture of lithium and lead. And why? So, as I mentioned, we can extract deuterium from the sea, but why lead? Because and lead, the isotope of lead, when it interacts with a neutron, will actually spallate if you have enough energy. And that means, what that means is that it will kick out another neutron. So I've now got 2 neutrons flying around. All right? So I've just made an extra neutron. So as long as I've got more than 8 mega electron volts of energy, this will happen. And fortunately, my neutrons, when they come out of a fusion reactor, have 14 MeV. So I've got the energy to do this. Wonderful. So then you take those neutrons, and this is where the lithium comes in. You make sure you have enough lithium. So those neutrons will react and produce, you'll get helium produced, but also it produces a tritium. Now, lithium-6 is, only makes up about 7% of the lithium that we get out of the ground. So there is actually another lithium reaction, the lithium-7 reaction, that we need to look at. But lithium, we've actually got quite a bit of lithium that can be extracted from the sea and other areas. We don't mine a lot of lithium right now, but we think that there's enough lithium reserves out there for us to make this work. And so it's this tritium here. So we've made 2 tritium for 1, so we've replaced our tritium. So we can get that back in, all right? So we've made our own tritium. And that lithium-7 reaction, okay, we are also making tritium, but we get some extra neutrons, which we can put back in and hopefully maybe get some more tritium being extracted. And this just is to tell you how much energy you need in order for that to happen. All right, so that's how we do it. And in this process, energy gets released, so that blanket heats up. It gets hot. And so that excess heat we can extract to boil the water or to heat up a gas or whatever that will now drive the turbines that will do produce the electricity. And so, this is just a standard, in the end, it becomes just a standard turbine system that we produce the electricity, and then we deliver it onto the grid. Okay? That's how a fusion reactor, hopefully one day, will do it. All right. 2 tokamaks, maybe 3, have achieved actual fusion, DT fusion. First one was a Princeton one, TFTR, tokamak fusion test reactor. I have been in the bay. Well, this reactor doesn't exist in there, but I have been in the bay. They don't have anything in there because it produced neutrons. It's mildly radioactive in there. You can only spend about 30 seconds inside there at a time. But I have been in there. So I've seen, it's massive, just how big that hall was. So they got about 10.7 megawatts that came out. The best I ever got was a Q of about 0.6. More recently, JET, which is a reactor in the UK. It actually was shut down earlier this year because it was getting to about 50 years old. It also got DT fusion to happen. It got to a Q of about 0.7 and was able to produce 16 megawatts. Now have a look at the temperatures. 500 million degrees. So we can get the temperature. Temperatures are easy. Actually, I think the world record is 780 million is the world record that machine's got. Now, in Japan, JT60, they never ran DT, but they ran a deuterium plasma to the fusion conditions needed. And what they say is that if you were to have run a DT reaction, they would have got the equivalent of a Q of 1.25, which sounds impressive, but in the science world, in the fusion world, we're like, if it's not DT, it doesn't count. You can't just say, but if. No, you got to do it to make it count. Impressive nonetheless what they did, but if you want to make this claim, do it in DT. No stellarator has achieved fusion yet. Maybe one day. W7X, which is our latest and greatest, and I was in Germany when they were building this, and Hydra, which back then was called Vega, was actually the bench. They benchmarked all the systems that went into this. Was done on our small machine. But they've got to the 100 million degrees. Obviously no Q because they don't do DT yet. But it's still very much a work in progress. There's another machine in Japan, LHD, which also, they won't do DT in that. That's going to get shut down in about 2 years' time and get replaced with something else soon. But they've also have achieved temperatures of 100 million degrees. And you can see these confinement times, they're not 1 second where we need them to be. And it's so difficult for us to get that. And that's where a lot of the work that we do is going into how do we get those numbers up. That's what we need to do. All right. And more recently, as I mentioned, the laser guys have actually managed to do it. So the National Ignition Facility, Lawrence Livermore National Lab, okay, it's massive. This is 3 football fields in size. You can put 3 football fields in that one room where this whole thing sits. And as I showed earlier, so it looks like that warp core of the Starship Enterprise, but that's inside there. That's the vacuum vessel where all the lasers come in and they do their magic. And that's sort of looking down through one of the laser paths down to inside the vacuum chamber. That's what the chamber looks like. Obviously, it's not under vacuum, someone in there, but it's really big. And since 2022 was when they got their first shot greater than 1. It was an actual DT shot, so deuterium tritium was in there. So they got a Q of 1.54, and so right up until this year, they've now increased that to about 2.36, which is probably about the limit for what they can do with the current lasers and that. They probably have to upgrade the lasers and that if they want to try and push for something more. But here's a thing about the Q scientific for the lasers. The lasers are very, very inefficient. So even though they're putting in 200 megajoules of energy in, the wall plug energy, what they need out off the grid to make that is somewhere between 300 to 500 megajoules. So their actual Q that they need to get in order to make the electricity, like enough energy to let's say sell on the grid, right, will need to be a Q of several hundred, not a Q of 20. So in some ways, they have a much larger engineering hurdle that they need to overcome to do that. Not saying they can't, but it's, but nonetheless, it's very impressive what they've done. Okay, and of course, we are going to try and do this with ITER. ITER is going to be the world's biggest experiment. It's a tokamak, and just to give you a size scale, there's a person right there. And I was there earlier this year. It's still under construction. These down here are my photos when I was there. That's the inside of the vessel. That's where the center stack will be. This is where they're making the coils. This is from the ITER website. But look at this. It's going to get to a Q of scientific of 10, halfway to where we need to be of Q equals 20. And this is why we need ITER. We need ITER because even though maybe a private company might get Q equals 1 before ITER, but ITER's going to get to Q equals 10. Going from 10 to 20 actually is probably, from an engineering point, will be easier to do. So it will be the first of the big tokamaks. And I've got a little treat here for everyone. I'm going to pass this around. So feel it, move it around. That is a piece of ITER. That is the tungsten, the inside of ITER, the wall that will protect the vessel and the coils and that from the plasma, from the 100 million degree plasma, is going to be made from that stuff. It's a very special type of tungsten. It's made in a very particular way. You'll see an arrow. The grain structure goes in a particular way. So that's that was made only for ITER. Only ITER will use that type of tungsten. So enjoy touching a piece of ITER. Why don't we have fusion power generated yet? So I'm getting on to the last part of my talk here. All right, what's holding us back? Plasma material interactions, the stuff that I specialize in. And basically, at some point, those ions, that plasma will interact with the wall. And actually, we deliberately make it hit the wall, a particular part of the wall inside a reactor called the diverter. It's our exhaust system. It's where we can pump things out, right? But the thing is, we're going to be dumping so much energy onto that surface that we're going to start doing some real damage to it. And we have to be able to either control it or understand it or mitigate it in some way. It's very complicated what happens. I teach several courses just basically explaining that one picture, right? You know, there's probably an infinite number of PhDs just in that one picture. So I'm not going to dive too much into it, but just know a surface will be changed completely by a fusion reactor. So, if the materials fail, they can be catastrophic. So if you have a look here, this is a machine in, this is D3D in San Diego. It's one of the big machines the US has at the moment, right? And you'll see that that plasma touches, this is the diverter down here, right? Down the bottom here, that's the diverter. So we're deliberately making that plasma go down there and touch the wall. UFOs do exist, but not with little green aliens. These little things down here that appear, we call these UFOs, unidentified flying objects, because we see them, but we don't know where they come from. And it comes from materials interacting with the plasma and failing, at some level. That stuff is getting ejected off the surface. And if it gets into your plasma, something like this happens. This is JET in England operating. So there's a plasma in there. And when you get a failure of the surface, boom. The plasma goes. All that energy that was in that has to go somewhere. And it goes back out into the coils and where all that magnetic energy is coming from, that goes into the plasma. And I've heard people talk about that when those types of what we call those instabilities, we call disruptions happen, that they've actually physically seen a machine of several thousand tons jump. That's how much energy gets pushed back, right? We have to stop those. We can't allow that to happen. So let's go back to basics again. Don't have to go as far as the Greeks this time. We go back to the sun. Why does the sun work? Why does it work? Gravity. Even more fundamental than that. Watch here. What happens out here? There's a solar flare. There's an instability, right? Instabilities happen. What does the sun not have? A wall. Doesn't have a wall. Stuff goes out and keeps going out. Doesn't come back in. So you don't get stuff coming back in that can potentially do something to the plasma. So we need to do something like that. Because if we got something that comes out of the plasma and hits the wall, okay, it will cool down to the temperature of the wall. If it's room temperature, you now have literally a cold gas that's coming back in, re-interacting with that plasma, which is sitting at 100 million degrees, but all that energy is now going to start going into that cold plasma to heat it up. So you have an energy drain that starts to happen with the plasma. And what that does is that you start getting pressure gradients, and those pressure gradients drive the instabilities that you see, like those failures. So what you can potentially get is damage like this. So the surface of the sun, if we look at how much energy per square meter per second there is, what we call the heat flux that's coming off the surface of the sun, all right? So joules per second, so watts, power. So it's about 60 megawatts of power, 60 million watts of power that the sun puts out. In a fusion reactor, we can have up to 1 billion watts per square meter hitting our surfaces. Tungsten, which I think this is that stuff, will melt at 10 megawatts per square meter. So we're already operating 100 times above, where the melting, where the energy is to melt tungsten are. So we have to design the machine so those heat fluxes are below that threshold. Now, we turn these things into liquid metals. The helium, if we don't get the helium out, can start to change the surface. We get something called fuzz. That tungsten will start getting like this kind of little fuzzy dust-like thing that happens that can actually get into your machine and becomes a big problem, okay? And recycling. And when I say recycling, stuff that comes off the wall gets redeposited elsewhere. You can see that these colors is redeposited material that comes from somewhere and gets redeposited. They're estimating that in ITER, there's going to be something like 1,000 tons a year of tungsten that will get moved around, that will get sputtered, blasted off the surface, and then moved around the machine by the magnetic fields and get redeposited. And if it deposits in a particular area, builds up, and interacts with the plasma, you can get these catastrophic failures happening. So our heat fluxes literally do exceed the surface of the sun. So the sun sort of sits about here, and a lot of we want to be down here where we operate, but right now with a lot of the instabilities and things like that, we far exceed anything that, that we can tolerate. And you saw from that previous slide that damage to that tile, right? We turned it into a liquid metal. So a whole bunch of people, of us, thought, why don't we just start with a liquid metal? Liquid metals give you some advantages, potentially. They're liquid, they flow, you can make them flow. Imagine having a flowing wall on the inside. Pretty nuts, huh? But it actually turns out to be actually quite easy to do. Now, so you can use that to do some heat removal. You can capture the particles right into your liquid metal and maybe transport them out, flow them outside of your machine, and then you can reprocess them outside the machine, keeping the inside clean of any impurities. Now you will get some other, you still will get some stuff coming out, but potentially, you can maybe deal with them if you choose the right liquid metal. So what do we want for it to be the right liquid metal, the correct liquid metal? Right? We want something to be as low Z as possible. What I mean by that, on the periodic table, everything has an atomic number. Hydrogen is 1, helium is 2, lithium is 3. We call that the Z of the element. So you can see here, this is actually a hydroplasma where one of our tiles is failing. We deliberately make it fail because we're trying to push it here. But the reason it's failing is because we actually had a low Z material in there. We actually had lithium in there. So we're giving away the story here a little bit. And it allowed us to operate our plasma we got about 5 times the energy into the plasma than what we normally would do if we didn't use it, which blew us away when that happened. We need something that has a high affinity for the things that come out. Again, lithium is that material. It's very reactive. It loves chemically to react with things. Turns out physically it will also capture things. We need it constantly flowing and refreshing. Okay, this is one of our systems, and if you do the tour, I'll have these out, and I'll talk a little bit more about how we flow liquid metals. But you can see here, we've got a flowing liquid metal, flowing lithium in here. Stable flow, we need to make sure that it will, if something hits it, that it's not just going to go splashing everywhere. So you need to engineer it in a way that even if you get one of these instabilities, it's not going to go splashing everywhere. And of course, it needs to be neutron damage tolerant. Those neutrons are flying around like little bullets, 14 MeV. Maybe that's the wrong word these days, but these things are zipping around and they're going to do a lot of damage to your surface. So a number of candidate materials, tin and lithium are probably the two main ones, but my argument is, if we look at how much tin we need inside the reactor, if we get a little bit in there and gets into the plasma, you only need about 0.01% of the tin to be in the plasma that it will radiate. It will get rid of 50% of the power that is in your plasma, rendering it basically useless. Whereas lithium is all the way up here. Okay, it means that you need to get more lithium, so you can tolerate lithium a lot more in your plasma. And so if you do that, it turns out that the difference in operating regimes, the temperatures, normally people will say, oh, you can operate tin at much higher wall temperatures than lithium, but when you take this into account, it's only about 75 degrees better. So our argument is, go to lithium. Just lithium, does much better things for you, and you can tolerate it much better than tin. So lithium is our material that we want to use. So it's number 3 on the periodic table. It's this nice silvery metal. If you hold it in your hand, it will go black, reacting to everything in about 10 seconds, and you'll feel some heat on your hand. It actually gets quite warm. It's got really good properties, thermal properties. It's low density. It's got a low melting point. But the really cool thing is that we can do some really interesting things. Even though its thermal conductivity is lower than tungsten, but because we can flow it and we can engineer some interesting geometries, we can actually get convective cooling that helps us, where we can handle heat fluxes with lithium higher than what tungsten can handle. And we don't have to worry about melting because it's already melted. Lithium can also produce this, what we call a vapor cloud, which makes this little cushion of vapor above the surface that also protects it, dissipates it, spreads the energy out over a larger surface area, bringing the watts per square meter down. And you put that together. So this here is an experiment I ran on a Chinese machine in 2020 called East. And you can see the lithium there, the green. That particular shot, we got to about 120 million degrees for about 10 seconds with it. So I had, for about 10 seconds, the hottest temperatures in the solar system, at least, as far as I can tell. And we did that for about 15 hours. We ran these experiments for 15 hours. So let's go back to this, this slide here, okay? And where are we in terms of all this? Well, we still haven't figured out how to separate the fuel we breathe, okay? We don't have a blanket yet. We're trying. We don't have a way to extract the neutrons and the energy from the neutrons. And we still haven't figured out how to make the actual electricity. You can see, we still have a long way to go, okay? And money makes the difference. Funding. This slide here tells you everything. If after the oil crisis in the 1970s, if funding for fusion had sort of, even if it stayed where it was and increased a bit, you can see here, different funding efforts, we would have had fusion by now already. We are right now, this black line. This is where fusion is, or was at least up to 2010. Right now, we're sort of getting back to this red line. 2025, this is where we are. We're only just getting back to there. And hopefully, our funding will keep increasing. Now, private fusion companies are helping that along. They're sort of pushing the federal government to continue, to continue increasing that. As of this year, 45 private fusion companies spread out all over the world. USA has by far the most number, 25. I work with several of them. And what's the next step? So I've only got a few more slides left here. What's the next step? Demo, the first demonstration of fusion power. Now, here's a kicker. We haven't even finished building ITER, right? We haven't finished building ITER. We're already starting to design. I'm on the design team for a demo already. I think that's pretty wild. And each country now is really looking at their own versions of what this demo will look like. ITER is a true international collaboration. There's about 45 countries involved in that. But demo is going to be, countries are going to go it alone. Once we understand ITER and learn everything from there, we're all going to be, it's going to be a race to see who does it first. All right, 2 more slides. The path towards commercial fusion. So we are sort of, this is where we've been going with the current machines that we have right now. So we're getting into the next step of fusion experiments where we're starting to do all the baseline stuff for ITER. All right, so we are here, 2024, 25. ITER is going to come online in the 2030s, probably operate for about 10, 15 years. We're going to learn a lot with that. And that will get us to demo, which will be our first prototype, and then eventually we'll hopefully start seeing commercial fusion reactors. Now, the private industry, is looking to do this a lot quicker. They want to do things about 10 to 20 years earlier than what this is sort of represents what the public, funding, what the governments want to do. So right now, this is sort of where we're at in terms of the private companies. It's really only 2 companies right now that I would say have legitimate machines that are doing, potentially doing, fusion type experiments. So you've got TAE out in California. I guess General Fusion in Canada, so 3. They're doing things, but Tokamak Energy in the UK, they've actually last year demonstrated 100 million degree plasma in their machine. And actually published it. The others tend not to like to publish things for some reason. And so from there, because they can scale things much more quickly, they want to have their demonstration plan sort of within 2030 and have their first commercial reactors on the grid by about 2040. That's where they're looking at doing it. And in the end, where does this take us? So, we've got ITER and demo down here. We want to have base load power. So we want to get to this point here. But once we get that, and once we have the technology, we can start engineering things to maybe get more smaller modular type fusion reactors, where we can maybe make them more transportable, miniaturize them, and we can have security. We can really push the security. Things like commercial security, not just military, help with disaster relief, security of the people, and planetary security. So things like ships, we'll be able to stick these on ships, right? So commercial security, we don't have to worry about oil and that. So it takes that aspect away. All right, disaster relief. Imagine, you've got a flood or a tornado that's come through, taken out the local grid. You can wheel one of these guys in, plug it in, that people can plug in and have power until the local grid gets back up online. Of course, military security, But the big one that a lot of people are starting to think about is planetary security. And that is dealing with if you've got an asteroid or a comet coming in. And really, why do you need a fusion engine, a fusion reactor for this? Well, comets are the speedsters of the solar system. We don't see comets until they get to about Jupiter. That's where they start interacting enough with the sun that they will light up and become bright. Beyond that, we don't see them. Thing is, when we see them at Jupiter, they can be, and if they're going to crash into the Earth, they can be to the Earth in under a year. Under a year. Right now, our technology, we can barely get to, well, we can't get to Mars, but the probes that we send to Mars take 9 months to get there, right? And we don't want to be blowing these things up near the Earth, right? It's not like Armageddon and those films, because if you do that, you're just going to be raining a whole bunch of bad stuff onto you. So you want to be able to intercept these guys out near the asteroid belt or out near Jupiter even. And so you need something that will get you out there fast enough. And fusion engines are the only things that will be able to produce the impulse, the thrust that you need to get out there in sufficient time to intercept things like comets. So with that, I will end it. I hope you enjoyed it. Thank you for your attention. These are just some of the people that I work with, our team here at the university and or our collaborators around the world. So thank you.